Morning, everybody. Thanks for coming. So it's a pleasure to introduce Andrey, who is giving 3 lectures this week. First this morning is about the generalized Skorokhod reflection.
Thank you, thank you. At first, I would like to thank organizers to inviting me here, and it's a great pleasure to be in Cambridge and to see a lot of great mathematicians. I've got a lot of new interesting ideas here, and I'll deliver 3 lectures on the following topics. Functional limit theorems for perturbed random walks. And my aim is to describe a diffusion in a media with semi-permeable membranes or reflected streams. And today I will discuss reflection problem. And at first, let me recall macroscopic model for the Brownian motion and Donsker theorem. Okay, let Sn be a random walk, just sum of independent, identically distributed random variables with 0 mean and variance 1. Well, we scale space n time n times space square root of n times and pass to a limit, and it's well known that this sequence converges in distribution to a Brownian motion, or sometimes I'll say Wiener process. And the global question is the following. Assume that you have some membrane. Assume that regularity of the random walk is violated on some, say, finite sets. For simplicity, imagine that all our random variables are integer one. Okay, there is finite set minus mm, and here you have regular behavior, say increments are IID, mean 0, finite variance, but when you enter the membrane, you have something different, maybe large jumps with heavy tails, some irregular behavior, but when you exit, again, regular behavior, sum of IIDs. And my question is, okay, let's make Donsker scaling, the same scaling, time n times, space square root of n times, pass to a limit and ask, what is the limit? Is it a Brownian motion or another process? Well, it is, it's clear that if the limit exists, then the process should behave like a Brownian motion everywhere outside of 0. Well, when you shrink the space, then all this membrane shrinks to one singular point. So you'll have a Brownian motion everywhere, except for 0, and you have some skew or some reflection or something at 0. And let me start with the following very simple warm-up example. Let's consider at first the simplest situation where increments are plus or minus 1s with probability 1/2. So we have simple symmetric random walk. Well, if you scale space-time, you get Brownian motion. And now assume that you perturb transition probabilities in 1.0. And the perturbation is the following. When you hit 0, then with probability 1, you reflect. So the next jump is above. So very strong perturbation. So you cannot go through 0. So assume that you have a wall here. And then you have these exits. Well, then regular behavior, then exit again. Well, everything is computable. So you can calculate transition probabilities and so on and so forth. And it can be easily seen that the distribution of this random walk is nothing else but just absolute value of this. So if you consider Donsker scaling for this, then what is the limit? The limit is just absolute value of a Brownian motion. And okay, so it's natural to say that this process is a reflecting Brownian motion. So just application of continuity principle. Now, let me consider another example. Well, this is the topic of my second lecture. And assume that zero is not reflecting screen, but semi-permeable. And you go up with probability P, and you go down with probability Q is 1 minus P. So sometimes you go up, sometimes you go down, and then you have simple symmetric random walk. So you have some irregularity only at zero. Well, in this case, you also can calculate transition probabilities for this random walk, and then show weak relative compactness, and then prove that finite dimensional distribution of these random walk after the scaling are convergent, and the resulting process is a Markov process with the following probability, transition probability density function. So look at the transition probabilities for the walk and transition probabilities for the process. Well, we expect that this happens. Yes. Yes. No, P goes up, always P goes up, and always Q goes down. No, I mean, just let me denote it, P and Q. No. No. I don't know the answer. Maybe it's simple, I don't know. Okay. But I would like to mention that when you consider reflected Brownian motion is just absolute value, a continuous function of initial noise. Here, this process is not a continuous function of W. And this is a big problem, how to write some equation for this Q Brownian motion. But today I'll consider only reflections, the simplest situation. And let us discuss again this approach. Well, psi were symmetric plus minus 1, and assume that psi are not symmetric, but expectation is 0. Then we will not have this. Another question. Okay, what happens if you can jump up not by 1 unit, but say 1 or 2 or 3? What is the limit? You cannot apply just continuity principle and say that the random walk has the same distribution as absolute value of something known. So we have to find another approach for proving results. Well, let me mention some important results. Just let me recall you the definition of convergence in distribution. So we'll say that a sequence of p-valued E is some metric space, random elements converge in distribution to psi 0 if for any function f, which is continuous and bounded, we have convergence of expectations. And usually the space E will be a space of continuous functions with a supremum norm or space of Cadillac, so functions that are continuous from the right and have a limit from the left with Skorokhod metric. And let me also recall you very important result proved by Skorokhod that states that if this E is separable metric space, and if you have convergence in distribution, Then you have another probability space and some sequence such that this theta n with tilde has the same distribution as theta n, and you have almost sure convergence. Well, another direction is obvious. If you have this, if you have copies, then you have convergence in distribution. But this helps because you can think that your sequence, if it is weak convergent, that it's you can work with analysis like in real analysis, fix omega, and you have just usual convergence. And one important result is continuous mapping theorem. Okay, assume that you have weak convergence, and we consider some function g of theta n. Well, if g is continuous, then from the definition of weak convergence, you have this. But it follows from the Skorokhod representation that g may be continuous almost everywhere. So if theta 0 belongs to some set of the full probability, and g is continuous everywhere on U and maybe discontinuous in some other points, then you also have convergence in distribution. So in some sense, G may be a little bit discontinuous. And my aim is to construct some reflective map, which is continuous, well, almost everywhere, or which is continuous for most of reasonable problems. Okay, and at first, let me recall you the classical Skorokhod reflecting problem. So the mathematical formulation is this, and let me explain you the Skorokhod reflection in informal way. So assume that you have a robot with some instruction or program, and time, space, and this is a program. So it says robot go up, go down, and assume that you have a wall at 0. So assume that I'm a robot and I'm walking here and there, and sometimes the program say go here. But there is a wall. I cannot walk, so I'm trying, and I'm staying near the wall. And then instruction says, okay, go other direction, and I go here, and then I follow instruction, go forward, go backward. Again, when I'm near the wall and I'm trying to go there, the wall pushes me other direction. So W is a program. So W is a program. X is, and the question is, find the position of a robot. And X is position of a robot. Well, when a robot tries to go down, you can say, okay, allow robot to go down, but you have to add the push of the wall. So I'm pushing the wall pushes to me. So if I'm going down, the wall pushes me other direction, and as a result, I'm staying here. But then my instruction says, okay, go up, and I'm going up following this direction, and so on and so forth. So position of a robot is a sum. It's instruction plus reflecting term plus L, and L is the push of the wall. And well, when the robot is here, the wall does not push the robot. So this means that L, this function L, may increase only when the robot is near the wall. Okay, and so this is not random. This is just deterministic problem. And Skorokhod proved that, well, there is a unique solution to this problem. And moreover, it can be shown that you can write a formula for L, for this L, and for X as a sum. And well, you see here the running, so-called running minimum of the input. Okay. well, this is just a picture. Blue is the program. Green is a position of robot, and red is L, is a reflection. So robot follows blue line, then it's near the wall. Program says, okay, go down. The wall pushes up, so robot stays. Then the program say, okay, stay near the wall. Robot stays near the wall. The program say, go up. It goes up, and so on and so forth.
So the W should be continued.
Originally, Skorokhod spoke about continuous function, but the same formula is for Cadillac functions. The same theorem is true for discontinuous. The same answer. So if W is a function that is continuous from the right and has left limit, you can ask the following problem. Find a pair of functions, x and L, such that x is non-negative, x is a sum of these two, and L may increase only when x hits 0, and that's all. And there is a unique solution, and the solution is given by this function. Yes? I think no, I think not. Well, you mean here you should have to write minus? Not. This is, I think, this is not true. Well, you cannot overjump if it is Cadillac, so you try to jump here. So so you have to add this, you have to add this, and so dl is because x minus is not 0. Yes, x minus is not 0. So I think this formula is correct. So x will be 0, and you multiply by dl, delta n. Okay, so I think the formula is, so this is correct formula. This is good question. For some domains and some reflecting fields, you can try to formulate similar problem and result. Okay, the question is, okay, you have W, optimal multidimensional noise. You have to find x such that you have to, this is reflecting vector field, V of x of s, dl of s, where this function is a function of bounded variation, and this vector field points inside. And sometimes, for example, if this space is convex, if this set is convex, and if reflected field is normal, say, you have uniqueness of the solution, Lipschitz property, or for example, so a lot of people study this question in domains with smooth boundary, in wedges, or in orthons, different type of reflections, say Harrison, Raymond, Leon, Schnittmann, Tanaka. So there are a lot of results. Sometimes you have uniqueness and nice properties. Sometimes it's a question. Today I consider, I think yes. There are some counterexamples, and it's a big problem how to construct a Brownian motion, say with oblique reflection. And okay, the point is the vertex, and there are necessary and sufficient conditions by Varadan and Williams, for example, in terms of these directions. Okay, and so the questions are, is the vertex hit in finite time? They have criterion for some directions, it's 0 or 1. And if you hit, there is a question for Brownian motion, not for arbitrary continuous function, but for Brownian motion. Is there a possibility to exit? And there are sufficient and necessary conditions that you may exit. And another question is, okay, assume that you can enter and exit. Is this process a semi-martingale? Sometimes not. Sometimes not. Okay, so let me continue. And let me show you one example from Kuhn theory. And its relation with Skorokhod reflecting problem. Assume that you have a server and you have some like bits of information. You process these bits of information, so you have some requests, and theta m is arrival minus departure. Assume that the first half of the unit of time, some requests arrive, and then you process. So it's like virtual processing. So server can process dn requests at the instant n. Well, assume that these are random variables and consider heavy traffic limits. So assume that expectation of this difference is 0. But what happens? Okay, you have some random walk here, and assume that you try to jump here. So what does it mean? This means that you can process more than you have. Okay, but you cannot have the negative number of requests. So you just you process all of them and you set 0. And recursion is the following. And well, you know that you have convergence of this random walk to a Brownian motion. And you can see that this model is just Skorokhod reflection of the random walk. And Skorokhod map, so this map, the W to X, is Lipschitz continuous. So by continuous mapping theorem, the result is Lindley recursion converges to a Brownian motion. Okay, one important remark. You can ask me, okay, you have absolute value of a Brownian motion, so one process, and you have this reflected process, which is Brownian motion plus this L. Is it the same object or not? And the answer is yes, it is. Yes, it is. They have equal distribution. Moreover, if you consider the pair and the local time of 0, symmetric local time of 0 of this process, local time at 0 of this process, then you also have equality in distribution. So that's why sometimes this process L, the running minimum, is called the local time process. But be careful. This process and this process are continuous functions of W. And well, this process is a continuous function of this. But the local time of 0, generally speaking, not. Generally speaking, not. Okay, and well, and now let me consider just the following question. Assume that you have that increments here have distribution psi, 0 mean, variance sigma squared, and when you overshoot 0, you have another increment, for example, positive. And you add these increments, so eta 1, eta 2, and so on, before you cross 0 again. And again, increments psi, then you cross, then increments eta, and so on and so forth. And make Donsker scaling and try to pass to a limit. The question, okay, what is the limit? Well, this is a model of internet shop. Assume that you have a stock and you sell some goods. Sometimes you are out of stock, but you sell just and say, okay, we will send you tomorrow or maybe in a week, so don't worry. So you accept all claims. But, okay, if you are here, then you don't have you do not have any goods, so you have to do something else. So you try to buy big batches of goods that may be random. So you are in a hurry and say, okay, who can sell me very big some batch? So usually you don't refill the stock to zero. No. Usually you have to be somewhere here. Because if you're here and if you have critical mode, then immediately you'll be below. And usually if you are in hurry, then the price is higher than the regular one. And now let's try to discuss what is the limit. Okay, above zero, it should be Brownian motion. And well, this random walk is a sum of two: regular behavior, okay, Brownian motion, plus some of random variables that belong to domain of attraction of alpha stable. And if we consider this random walk and divide by, say, n to the power 1 over alpha, then we obtain alpha stable subordinator, which is discontinuous. And or if you take another scaling, you may see only three possibilities: alpha stable subordinator, or zero, or infinity. So the limiting process should be Brownian motion with something at zero, or some discontinuous exit, jump type exit, or no limit, infinite exit from zero. And the question is, okay, what is the limit? And but at first, let me describe the possibility. So what it can be? For example, assume that you have a strong Markov process, non-negative, and that behaves like a Brownian motion above zero. Well, its generator should be like 1/2 times second derivative everywhere except of zero. And it was proved by Wenzel, Feller, that there should be some boundary conditions. There are three non-negative numbers, P1, P2, P3, and sigma finite measure, P4. Well, P4 may be zero. So all of these numbers, so all of them cannot be zero. So at least one of these P1, P2, P3, P4 is non-degenerate. And well, there is a probabilistic meaning of this. For example, P1 is responsible for killing. So if you come to zero, the probability is killed. So we consider only conservative processes, so P1 will be zero. So P2 means reflection. So if you consider U prime of zero is zero, this boundary condition means Skorokhod reflection. This P4 is responsible for jump exit from zero, but be careful, P4 may be infinite. And this is intensity like intensity of Levy process. And P3 is some stickiness at zero. So when Brownian motion hits zero, okay, zero is some sticky point, then the sticky reflected Brownian motion can spend positive time at zero. But okay, it's not like you can't spend positive time. No. The set of zeros will be nowhere dense, but of positive Lebesgue measure. Positive Lebesgue measure. And now let me explain you how to construct this stickiness or jump exit, and maybe write some formulas. And well, at first, let X be a strong Markov process that visits 0 or some fixed point, say, okay, 0 with probability 1, and assume that L of t is a local time at 0. Let's consider the following continuous additive functional, just time plus rho some parameter times the local time at 0. So this function is continuous and increasing. This is just inverse. It is not 1 over, it's the inverse function. And let us consider this process X at this time. Well, L increases only when the process hits 0. So the flow of time is uniform if you are outside of 0, and you have some stickiness, you have some delay at 0. And from the general theory of Markov processes, it can be shown that this is again a Markov process, but this process spent positive time at 0. Well, for example, if you have reflected Brownian motion, okay, L is, I mentioned that L is the local time of X, the definition of this, and this process is called sticky reflected Brownian motion. And okay, I also mentioned that this process reflected, like Skorokhod reflected, is a continuous function of a noise. And this process is not. So if we use Skorokhod approach, we may use continuous mapping theorem, but if you take this process, okay, and write some stochastic differential equations, you have a problem because it was proved by Chitashvili and then by Engelbert and Peshker that sticky reflected Brownian motion satisfy, okay, some SDE, and the solution is not strong, but only weak. Okay, yes. Mm-hmm. Okay, you have, this is 0, and I think you have combination of these two, P2 and P3. Reflection plus delay. Reflection. So P3 over P2 should be is rho or 1 over rho, something like this.
So it is naive to think that exponential.
Yes, it is naive, but we will discuss this exponential times today. Okay, and now let me discuss jump time exit from 0. And so what I want to, okay, I have some input function W, and assume that you have some function, strictly increasing function F, that may be Cadlock. And let me write some generalization of the Skorokhod problem. So X is input, F is responsible for exits from 0, and you have to find L of t some inner time such that Y is a sum of input plus reflection. And this function L it may grow only when the process hits 0. Well, it can be proved that there exists a unique solution to this equation, and this solution is given by this formula. So this is the deterministic function. And well, if X is Brownian motion and well, this M is a running minimum, then you may meet the following. And for example, assume that F is alpha stable subordinator. Alpha stable subordinator. You may need this formula in the theory of continuous branching processes with immigration. Yes? I don't know. I don't know. Well, okay. So I found this is deterministic result. Yes, this is deterministic result. Well, and the proof of existence is just straightforward. Is just you have a formula you can plug and calculate.
X.
Yes, X has no negative jumps, and F is strictly increasing. Strictly, and nothing more. And uniqueness is proved, well, in more or less classical way. You have to, well, assume that there are two conditions and two solutions, and y1 and y2. Then you consider the difference of y1 and y2, and okay, but X is the same, and this difference is equal to f of L1 of t minus f of L2 of t. And observe that this function is a function of bounded variation, of locally bounded variation. And let's write that sphere of t. And okay, you have to write like integral from 0 to t to z of s dz of s minus sum of jumps, squares s less than or equal to t. And then you observe that this is integral. So that is y1 minus 1 y1 of s minus y2 of s. And dz is equal to this difference. So let me write df of L1 of s minus f of L2 of s. Okay, this is positive, this is negative, and let me show that this is negative. Really, this function and this function may grow only when the process y1 or y2 hit 0. Assume that y1 hit 0. Okay, assume that this is 0. Then, well, y2 is greater than or equal to 0, and this is less than or equal to 0. If y2 is positive, then this does not grow, and this may grow. So in this case, increment is negative. Okay, and if y2 is 0 and if this is greater than 0, you do the same reason. So this integral is less than or equal to 0. So this is less than or equal to 0. What does it mean? That is 0. So you have uniqueness. And well, this formula. So I don't know who wrote this formula first. I found this formula in the book of Blumenthal Excursion of Markov Processes, where he, well, in his case, in Cadillac functions, in Cadillac, yes. Well, it is important. You may not have, yes, it's important. Yes, it is important. There may be no solution. There may be no solution. So if the solution exists, then it is unique. But I think it may be no unique solution. Maybe no. So I think this is important. But I'm not sure. But in my models, for pre-limit models, you will see some processes that can overjump 0. But in a limit, no negative jumps. Well, in Blumenthal's book, X was Brownian motion and F were subordinators. Well, and now I would like to introduce some switch model, like pre-limit model for reflections. Okay, you have a noise. You have a noise, so this blue function, and some regulator. It's responsible for some reflections. So this blue function will converge to a Brownian motion, say to a Brownian motion, to some continuous process. And this red, say, alpha stable subordinator. And let's fix some small number delta and take the first part of this blue line and wait before you cross some critical level minus delta. Then you take first part of the red line. Then again, you behave like noise, so this part. Before you cross or hit minus delta, then again, you turn on red and so on and so forth. So yeah, you just cut blue and red into pieces and glue them together in some order. And then let's assume that this blue converge to a continuous function, for example, to a Brownian motion, and this red converge to some increasing function, say alpha stable subordinator. Well, this f prelimit may be discontinuous, they may be not increasing, and x also may be discontinuous. And then send delta to 0 and try to pass to a limit. And okay, with Andreas Ranze, we got the following result. Assume that sequence of non-random Cadillac functions converge in the Skorokhod space to a limit function x0, and assume that x0 does not have negative jumps. We assume that this sequence fn converges to some increasing function. And we assume that this delta, this gap, converges to 0. And okay, there is one technical condition about points of growth of this f, of jumps of f and level of constancies of running minimum. So M0 is running minimum, like in Skorokhod problem. Well, for stochastic processes like Brownian motion, Levy process, usually this E is satisfied because this set of jumps is countable. It's countable, and usually for nice processes, say independent, if you have countable numbers, usually with probability 1, you don't have intersection. Okay, well, and we also introduce some parameter rho n. Rho n is like speeding of a time or slowing of time of this fn. So if rho is 0, this means that we increase the time of f very, very fast. It's almost immediate. And infinity means slow down. So actually, rho is 1, rho is 0, and rho is infinity are interesting, but rho between 0 and infinity without 0 and infinity is the same as just rho is 1. And the answer is the following. Okay, if these conditions are satisfied, then if rho is 1, then you have this generalized Skorokhod reflecting problem. If rho is greater than 0 and less than infinity, then you have generalized Skorokhod reflecting with stickiness at 0, And if rho is infinity, then you hit 0 and live there forever. So you stay at 0 forever. Okay, now let me consider, yes? No, here. Yeah, here. So you use this regulator. So Fn itself converges to F0, but we may speed up or slow down for this Fn. Yes, and if, yeah, this is still deterministic. And so you see, this is continuous map. And now I would like to apply this continuous map to many situations. If I have a time, then I'll show you a sketch of the proof, but let me show you a few examples. For example, okay, the first example. Assume that you have a Brownian motion. So this is, so xn is x, so just Brownian motion. And you do the following. You select level delta. You hit negative delta. Then you have uniform motion up. Then again, Brownian motion, you hit again this, and so on and so forth. So if you glue together this part, and this part, you'll get the Brownian motion. So it's all the same to say that we start some Brownian motion, or you glue them together and say, okay, you cut Brownian motion into pieces. And then you send delta to 0. And okay, xn is a Brownian motion. x0 is a Brownian motion. This function f0 is just linear function. And in the limit, you'll get a sticky Brownian motion. Well, if you consider like arrays, like series, and if we have delta n and an and this angle, so the slope, if the slope converges to plus infinity, then you have just reflected without any delay. But if you have constant slope, then the answer is sticky reflected Brownian motion. Oh, I forgot to mention the following thing. When you consider this function, if f is continuous and increasing, then f composition of these two is just identity, and you get just regular Skorokhod. But for this formula is interesting only if f is discontinuous. Okay, and now let's consider a perturbed random walk. Regular behavior, IID mean zero, variance sigma squared, and eta belongs to domain of attraction of alpha stable law. Okay, I don't have a time, but this problem, when you have, say, regular behavior above zero and irregular below, okay, this random walk is just this switch problem I introduced with delta is zero, And okay, the Donsker scaling is just a solution of our switch problem. But you see, the scaling for S eta is not square root of n. It should be like n to the power 1 over alpha, well, times some slowly varying function. So for simplicity, I don't write it. I don't write it. So if you wish to divide by square root of n, you have to write n to the power alpha over 2. And here you have n. So n is n to the power alpha over 2 times rho n. And in this case, rho n is this, and it converges to 0. So in a limit, you have this process. And the short example is a storage process, and you'll see exponential distributions. So assume that the prelimit model is this. Decay with a constant speed. You wait exponential time with some parameter lambda, and sometimes you jump up, and this is sub. Then again and again and again. Sometimes it's called dam process. So you have water, this is rain, water is evaporating. Okay, if you have 0, then you stay at 0, say exponential distribution with parameter. Okay, it's with another parameter, lambda hat. And you exit, well, and the distribution is zeta. And again, you have this process, and these jumps have the same distribution as xi. These times are exponential with this parameter lambda, and here with another. We see that this model is, again, switch model. So let me write here red. So you wait here red and some exit. So this is input, this is reflection. So if you have some balance conditions, then this process converges to, say, a Brownian motion with a drift. And well, if you have another condition, for example, this with some balance between this gamma n and this lambda and this intensity, okay, then you have a sticky reflection of this Brownian motion with a linear drift. So it is simple consequence of my theorem. For example, if psi n k is just psi k over square root of n, then, well, assume that they have finite second moment, and if A is expectation of psi k, okay, and then you may take lambda n, and these are n, probably square root of n a plus mu. And well, you may ask, what about this condition? Okay, assume that zeta k has the same distribution as psi k. Everything is IID. Then gamma n should be like this, square root of n over a. If you take this gamma n, then you have convergence of this sequence to the uniform to identity function, and you'll get the sticky reflection in a limit. Okay, that's all for today. Thank you for your attention.
My coefficient is 3. You can't always continue.
My coefficient is 3.
So they're talking about sticky. Okay.
Ah, yes, I can.
Yeah, it's fun.
Yes, exactly.
Plus,
Yes, it can be calculated explicitly. Yes, you're right. Yeah. Rho is the limit of this. It is, if the limit exists, if 0, then instantaneous reflection, infinity, then 0 is, so you hit and never exit. Between 0 and infinity, so this parameter of stickiness, yes? You mean of processes, of one-dimensional distributions? Well, yeah, it's really interesting, but I don't know, because you see in the formula, you have this generalized inverse. So it is not... this one. So you have explicit formula for the limit. Well, I don't know. So I don't know. This is interesting question, but well, this map is not like Lipschitz continuous. So it is not Hölder continuous. It is discontinuous for some f0 and x. Well, in case when you have Brownian motion and Levy subordinators, this condition E is satisfied for free. But really, I don't know how to couple, say, different noises and to estimate Wasserstein distance. Yeah. So probably it can be proved that you have convergence in Wasserstein, but the interesting thing is how to couple, how to find some estimates. Yes, sure. if you have two bounds, there is no problem because the problem is when you have accumulation point. If you don't have accumulation, if you have two bounds, then you don't have. You can solve the problem here. When you first hit this bound, you start from the very beginning, and that's all. Ah, you mean here? You mean if you have two bounds, and if you want to overshoot everything, and this overshoot is very, very big, you have to reflect it here, but you reflect, okay, I don't know. Yeah. Without these big jumps, it's not a problem. So, and the problem so usually you don't have too many big jumps. So you have only finite numbers. So well, okay. Yes, this function, it doesn't have negative jumps. So if you have another screen, then you shouldn't have positive jumps. Well, it is interesting question how to do this if you have big negative jumps and how to reflect. Well, I have some ideas, but I don't know. So this is really interesting. No. We introduced delta because of the following reason. For example, if you have a Brownian motion and you have to reflect somehow at zero, then you cannot say, okay, you hit zero and you have some negligible, some very small jump if f is continuous, because well, behavior in a neighborhood of zero is very, very irregular. So you'll have too many crossing. This delta say, okay, if you hit this negative delta, then there is some positive time. But actually, for random walks, when you have piecewise linear, or like in that DEM model, you may take delta zero. So you hit and you start a new process. But the new process should also be like, you have to spend some positive time at zero. So this delta was introduced only to prevent some cases when, for example, the process about pushes down and this pushes up, and you don't know, should you use this or this, or how to interact? In this theorem, not, but well, I would like to obtain something like Walsh-Brownian motion with the same approach, and with rho depending on time, and maybe with some jumps. Well, the paper by Barry Akhtar that you sent to me has some formula for continuous time. Well, but when he constructed Walsh-Brownian motion as coupling of some independent linear processes, but I think this formula has deterministic nature, and you can prove some deterministic theorem with. So my aim is to have some rho that may depend on time too. No, not tomorrow. Thursday. Okay, but if you say tomorrow, I can deliver one more lecture. just tell me the topic. Diffusions with semi-permeable membranes, and I will talk about skew Brownian motion and Walsh-Brownian motion. So skew Brownian motion is the following process on a graph, such that here the behavior is Brownian motion with some switching at 0. And a skew Brownian motion is a particular case when excursions select direction of exit from 0 with probabilities P and Q, but also you may write these diffusions as some SDEs with generalized drift at 0. Generalized drift like delta function, delta function at 0. Yeah, it will be Brownian motion here. So in a limit, it will be Brownian motion everywhere with some switch at this point. So one-dimensional Brownian motion with one common point. And I'll consider I'll consider macroscopic approach. So I will consider some random walks, for example, random walks in on integers with some irregular behavior at some finite set. Then I make Donsker scaling limit, and in the limit, skew Brownian motion will appear. Or if you have different variances here and there, then in the limit there will be skew oscillating Brownian motion. So the variance here will be, say, sigma plus, the variance here below 0 will be sigma minus plus something at 0.